Welcome back students. So first start Brahmana. So last class we have studied about what is electrolytic conductance and resistance, what is equivalent conductance, what is specific conductance, and what is the relation between specific conductance, equivalent conductance, what is the relationship between molar conductance, equivalent conductance, etc. Next, let us discuss what are the factors which depends, what are the factors which affects the electrolytic conduction. So factors affecting electrolytic conduction. So first, nature of electrolyte. So if the electrolyte is a strong electrolyte, then its conduction power is more because it ionizes almost completely. But if the electrolyte like acetic acid, formic acid, various organic acids are there, and bases like ammonium hydroxide, the electrolytic conduction is generally less because they ionizes slightly. Okay, so due to formation of more number of ions, then so for strong electrolyte, the electrolytic conduction is more. The electrolytic conduction is more, and for like what is the strong electrolyte? You know, different salts, different acids, strong acids, strong bases. For that, the electrolytic conduction is more. Whereas for weak electrolyte, the electrolytic conduction for your ammonium hydroxide, acetic acid, etc., the conductance power is low, yet the conductance power is generally high because they ionizes almost completely and they ionizes slightly. Next, another factor on which this depends, that is your nature of solvent. If the solvent is polar and less viscous, then it can keep the ions apart from each other. In this way, the mobility of ion is more, and if the solvent is polar, the ionization of this electrolyte takes place easily. In this way, if the solvent is polar, the conductance is also more. For example, if we take water as a polar solvent, then the solution of sodium chloride, hydrochloric acid and sodium hydroxide, etc., that gives you high conductance value. But if we take different non-electrolytes, non-polar solvents, then the electrolytic ionization of these substances takes place, and generally the conductance value is very less. Okay. Next, another factor on which it depends, that is temperature. So with increase in temperature, the movement of ions increases. As the temperature increases, the movement of ions increases as well as ionization increases. So with increase in temperature, ionization increases as well as movement of ion increases. Hence, with increase in temperature, the conduction increases. A conductance increases. Conductance increases. Next, another factor, that is concentration. So if the concentration is more, then the conductance is low. Okay, in general, if the concentration is more conductance power. So more is the concentration, less is the conductance power. Okay. So why this happens? One thing, for weak electrolyte, if the concentration is low, if concentration is high, then what happens? The ionization becomes less. If the concentration is high, then the ionization becomes less. Hence, conductance power is very less. Similarly, in case of strong electrolyte, if the concentration is high, then the inter-ionic distances generally becomes less. Hence, with increase in concentration, the conductance value generally decreases. More is the concentration, less is the conductance value. That means if you dilute it, then the conductance value increases. So from that, from this concentration point, what we conclude? From that we conclude that on dilution, the conductance value increases. As with increasing concentration, the conductance value decreases. Similarly, dilution or with increase in dilution, increase in dilution, conductance increases. But here we have to know that three conductance values. One is equivalent conductance, molar conductance, and specific conductance. So the equivalent conductance and molar conductance that increases with dilution, whereas the specific conductance decreases with dilution. Okay. So remember the equivalent conductance and molar conductance. The equivalent conductance and molar conductance increases with dilution. So why this increases? Because with increase in dilution, so if more amount of solvent is added, if more amount of water is added, then the ionization of the electrolyte increases. As the ionization of electrolyte, for in case of weak electrolyte, ionization increases, and in case of strong electrolyte, the inter-ionic distance increases. In this way, movement of ion increases, the equivalent conductance and molar conductance increases with increase in dilution. But the specific conductance, that is our kappa, decreases with dilution. So the specific conductance decreases with dilution. Why? Because you know the specific conductance is the conductance value of 1 ml of electrolytic solution. The conductance value of 1 cm cube with the electrolytic solution is known as specific conductance. So as you diluted the solution, then the number of ions per unit volume decreases. So it depends on the number of ions. So the number of ions per unit volume decreases. Hence, specific conductance decreases with dilution. So why this decreases? Because number of ions per unit volume or unit cm cube, number of ions per cm cube or unit volume decreases. As the number of ion per unit volume decrease, or the number of ion unit volume means 1 ml, or we can say 1 cm cube. As the number of ions per unit volume decreases, the specific conductance decreases with dilution, whereas the equivalent conductance and molar conductance increases with dilution. Okay, clear? Now next conclude. How this conductance, equivalent conductance or molar conductance depends on dilution. So the quantitative relationship between this dilution and the equivalent conductance for weak electrolyte is generally given by Kohler's law. Okay. So now let us discuss what is Kohler's law. Ohler's law. First, let us discuss what happens to dilution of the conductance value. So, for strong electrolyte, generally with increase in dilution, the inter-ionic distance increases because solvent remains at that time. The distance between different ions increases. So in this way, the conductance value increases, and the relationship between this conductance value and this concentration is given by dy Hooker and Onsager. That is the equation lambda mc equal to lambda m naught minus a n root over c. What is this lambda mc? This is the molar conductance at any concentration, and this lambda m naught is the molar conductance at infinite dilution, and a, this is known as your this is the different nature. This depends on a is a factor that depends on nature of the solvent and the electrolyte, and C, this depends on the concentration of electrolyte. Okay, so this is a straight line type graph. Lambda is a linear, this gives a straight line, so linear. So experimentally, when the equivalent conductance and concentration when the molar conductance of an electrolyte, here lambda m of an electrolyte is taken, and here concentration, square root of the concentration is taken, then what happens? For strong electrolyte, it gives a straight line like this. So you know y equal to mx plus c system. So in this way, it gives, so its value becomes like this. But when the concentration is very less, it approximately becomes like this. Here suppose some example of a strong electrolyte, potassium chloride is taken. So when we draw the molar conductance value and square root of this concentration, at that time we get this type of a linear line. So in this way we get this type of linear line. But if the concentration is very less, then approximately it becomes very much linear. So if here the concentration is more, here the concentration is at the higher concentration, it becomes like this. At lower concentration, it becomes almost linear. So at lower concentration, it becomes almost linear. So when the concentration increases, that means dilution increases in this way. So when we add more and more amount of the solvent to the electrolyte, when we add more and more amount of electrolyte, so that its concentration approaches zero. When the concentration and the concentration approaches zero, then what is the conductance value of that? So you know, generally on dilution, the conductance value increases. Dilution in this way, concentration in this way, so the conductance value increases. On dilution, the conductance value increases. So when the concentration approaches zero, limiting value, it becomes, so here it is the highest conductance value. So here we get the higher conductance value. So in dilution, we get the highest conductance value. But if we consider about an weak electrolyte, then so first it has very low value at low concentration. But when the concentration is generally diluted, when more and more amount of when more and more amount of electrolyte is added to it, more and more amount of solvent is added to it, then we get this type of graph which sharply increases. On dilution, it sharply increases. So for strong electrolyte, what is the conductance value at infinite dilution? What is the conductance value at infinite dilution? So this is for acetic acid. Okay. So what is the conductance value at infinite dilution for a strong electrolyte can be found out by extrapolating this graph. By extrapolation of this graph, we can find out what is the conductance value of a strong electrolyte experimentally. But when we consider about the weak electrolyte on dilution, it increases sharply. So in this way, we cannot find out what is its limiting conductance value at infinite dilution. what is the conductance value of this weak electrolyte? That cannot be determined. That cannot be determined by extrapolating this graph. So by extrapolating the graph, the conductance value of strong electrolyte can be known, but the conductance value of molar conductance of weak electrolyte cannot be drawn. So to overcome this problem, Colas postulated a law. Colas formulated a law that is known as the Colas law. So before proposing this law, what he said, what he do? So before proposing this law, he had taken some strong electrolyte containing some common cation and some common anion and find out what is the conductance value of that electrolyte. For example, when we take the conductance value of potassium chloride, sodium chloride, potassium nitrate, sodium nitrate, and we find out the difference between the conductance value of two. So what is the difference between these two is equal to same. Suppose this is conductance value equal to A, and here also we find the same value. That means it does not depends on the electrolyte, it depends on what is the ions present here. So look here, as the difference here is same, as the difference here is also same, from that we concluded that this potassium and sodium ion has some common conductance value. So that when we find out the difference, this chlorine cancels, or this nitrogen cancels, and the conductance of potassium and nitrate give rise to Ab. Similarly, we take some electrolytes like potassium nitrate and potassium chloride, sodium nitrate and sodium chloride. So in this case the cations are same and the anions are same. Suppose here the conductance value we found V, and here also we found the same conductance value V. That is 2 point something, and here 23 point something the conductance value, and here the conductance value 2.69 like this. So in this way, same numerical value, what the numerical value found here. So from that, what he conclude? From that he concluded that these are the same cations. Here the same cations, only the anions are different. As the anions are different, we get the same conductance value. As the cations are different, we get the same conductance value. From that, he concluded that every cation has a particular conductance value at infinite dilution, and every anion has a particular conductance value at infinite dilution. So from that, he concluded that every cation and every anion has a particular conductance value. Okay, so every cation and every anion has a particular conductance value. And to this conclusion, he formulated this law. And what is that law? The law states that at infinite dilution, when the dissociation is completed, each ion makes a definite contribution towards molar conductance or equivalent conductance, irrespective of the other ion of the other ion with which it is associated, and the total molar conductance or equivalent conductance is the sum of contribution of each ions. Sum of contribution of each ions. Okay. So what is this? So at infinite dilution. So when that is called limiting molar conductivity. At infinite dilution means when the dissociation is complete. That means the concentration approaches zero. So at infinite dilution, or when the concentration approaches zero, and when the dissociation is complete dissociation of the electrolyte takes place, whether the seed is a strong electrolyte, whether this is a weak electrolyte, but the dissociation is completed at that ion. So each ion makes a definite contribution towards equivalent conductance or molar conductance, irrespective of the other ion with which associated. And the total equivalent conductance or molar conductance of the electrolyte is the sum of equivalent conductance of or sum of molar conductance of each ions, or the sum of contributions of cations and anions. Or we can say the limiting molar conductivity of the electrolyte is the sum of contributions of its cations and anions multiplied by the number of cations and anions that is given by one formula unit of the electrolyte. Okay. So this is known as your Colar's law. So we can also define that. What is that? So we can also define the limiting molar conductivity. The limiting molar conductivity of an electrolyte is the sum of ionic conductivity, of ions, sum of conductivity of each ions multiplied by the number of ions multiplied by the number of ions given by one formula unit of the electrolyte. So we can see the alternative method, alternative definition, same thing, just language different. Okay, so limiting molar conductivity of an electrolyte is the sum of ionic conductivity of each ions multiplied by the number of ions given by one formula unit of the electrolyte. Okay, so actually whether suppose you consider about acetic acid, it contains CH3CO minus ion and H plus ion. So whether this acetate ion, actually what is this meaning? This means that the acetate ion has a particular conductance value, whether it linked with H plus ion, whether it linked with Na plus ion, whether it linked with K plus ion, any ion. Similarly, the K plus ion has also a specific conductance value at infinite dilution, whether it linked with OH minus ion, whether it linked with Cn minus ion, whether it linked with NO3 minus ion. That means every ion has a independent conductance value, whether this is a cation or anion. So every ion has a independent conductance value whether it linked with any other ion. So every ion has a independent, every ion has a independent conductance value. Every ion has a independent conductance value whether it linked with any other ions. That means whether K plus linked with the Cl minus or nitrate ion, NO3 minus or OH minus ion, but the K plus has a same conductance value in every case. Similarly, Na plus has conductance value in every case is same. Similarly, NH4 ammonium ion has a conductance value, the limiting conductance value, or it has conductance value at infant dilution is same whether it linked with Cl minus ion, whether it linked with OH minus ion, whether it linked with Br minus ion, etc. So that means independent conductance value. In this way, this law is also called law of independent migration. This law, Paul's law, is also called law of independent migration. This is also called law of independent migrations. Okay. Then what is the mathematical formula of this law? So in terms of molar conductivity, lambda m naught. So this is represented as naught, or it may be represented as lambda m infinity. Infinite dilution or when the concentration approaches 0. That means we can say lambda m naught, or you can write lambda m infinity. So lambda m naught or lambda m infinity for a electrolyte, for an electrolyte AXBY equal to lambda m naught x number of AY plus is the cation plus lambda m naught of Y number of B x minus. Okay, so this is your molar conductance value. Similarly, this is for molar conductance. When you consider the molar conductance, when you consider the molar conductance, when you consider the molar conductance, then this is the mathematical formula. Similarly, when we consider equivalent conductance, when we consider equivalent conductance, what is the formula? The formula is that lambda E cube naught of, suppose this all is lambda E cube naught equal to lambda E cube naught of A Y plus lambda E cube naught of B x minus, or simply lambda E2 naught lambda E2 cation plus lambda E2 anion. Okay, so lambda E2 naught equal to lambda E2 cation C plus A minus. This is cation, C stands for your cation, A stands for anion. So this is the mathematical formula of Paul's law. This is the mathematical formula of this is the mathematical formula of Paul's law. Okay, now you are clear. That means every ion has a particular conductance value whether it linked with any type of ion, irrespective of the other ion with which it is associated. Okay. Now, what are the applications of Paul's law? Now let us discuss the applications of Paul's law. So first, it is helpful to infinite dilution. So it is helpful to calculate. It is helpful to calculate the equivalent conductance of weak electrolyte at infinite dilution. So we know we cannot determine the limiting molar conductivity or the equivalent conductance as well as molar conductance. We know we cannot calculate the equivalent conductance as well as molar conductance of weak electrolyte at infinite dilution. We cannot determine experimentally the conductance value of the equivalent and molar conductance of weak electrolyte at infinite dilution. But this can be calculated by using the equivalent or molar conductance of strong electrolyte in terms of some strong electrolyte. So it is helpful to calculate the equivalent conductance or the molar conductance. Molar conductance. Equivalent conductance or molar conductance with electrolyte at infinite dilution, which cannot be determined experimentally. For example, suppose you consider the molar conductance of acetic acid at infinite dilution. We know this molar at infinite dilution, what is this value? That is equal to lambda m CH3CO minus plus lambda m H plus lambda m of H plus. Okay, but this cannot be determined experimentally, but this can be determined in terms of some strong electrolytes. Like, look here, I can write lambda m CH3CO minus plus lambda m Na plus lambda m H plus lambda m Cl minus lambda m Na minus lambda m Cl minus. So this lambda m Na plus lambda m plus minus is there and this plus minus is there. These two can be cancelled and lambda m H plus. So then Na plus will cancel and then this. So here I have added lambda m Na plus lambda m Na plus added and subtracted. Here also I have added lambda m Cl minus and subtracted lambda m Cl minus. In this way, what we can, that is equal to lambda m CH3COO, that is equal to, suppose these two are added, lambda m CH3CONA plus lambda m HCl minus lambda m NaCl. So all these things are at infinite dilution. Okay. So in this way, if we cannot determine this weak electrolyte experimentally, this can be determined by using the molar conductance of some strong electrolyte. So Cohn's law is applicable to calculate the equivalent conductance and molar conductance of weak electrolytes in terms of some strong electrolytes. Okay, we will discuss this by giving some numerical problems. Again we will discuss after that some numerical problems. So this acetic acid can be determined by using the molar conductance, the limiting molar conductance of sodium acetate, hydrochloric acid and sodium chloride. Okay. Now this is also helpful to determine the degree of dissociation. This Cohn's law is also applicable to find out the degree of dissociation. To determine the degree of dissociation. So by the degree of dissociation alpha by the formula lambda mc by lambda m. So this is lambda m naught. This is the molar conductance at infinite dilution, and this is molar conductance at any concentration. So molar conductance at any concentration and molar conductance at infinite dilation. These two ratio gives degree of dissociation. And this is also helpful to determine. This is also helpful to determine the dissociation constant of a electrolyte. To determine the dissociation constant of an electrolyte by the formula dissociation constant alpha C alpha square by 1 minus alpha. So this dissociation constant of the weak electrolyte can be determined by the formula C alpha square by 1 minus alpha, where the C represents the concentration and alpha represents the degree of dissociation. C that represents concentration, molar concentration, that is your molar concentration, and alpha is the degree of dissociation. That is the degree of dissociation. Okay. So this is your applications of Collard's law. It is also helpful to determine the solubility product of sparingly soluble salt. It is also helpful to determine the solubility product of sparingly soluble salt. Okay. So this is the applications of Collard's law. Now let us discuss some related problems. Okay, so first calculate lambda and naught for CaCl2 and NgSO4 from the following data. So all these given Ca2 plus Ng2 plus Cl minus sulfate minus. So we know if any molar conductance of any electrolyte is the sum of molar conductance of its cations and anions and multiplied by the number of ions. For example, suppose aluminum sulfate given. Look here, just look at the example. Suppose aluminum sulfate given. Then what is the molar conductance of this? So you have to calculate the two number of, for calculating this molar conductance lambda and naught of this two number of lambda and naught of Al3 plus 3 number of lambda m naught of sulfur 2 minus. In this way you have to calculate the molar conductance. So CaCl2. So in this case lambda m naught of CaCl2 equal to lambda m naught of Ca2 plus lambda m naught of Cl minus multiplied by 2. So in this way put these values, that is 119.0 plus 2 into 76.3. So here the answer you get, that is equal to 271.6 Salmon Cm square mole inverse CaCl2. Okay. Similarly, lambda and naught of NgSO4. Simply this is equal to lambda and naught of Mg2 plus lambda and naught of SO4 2 minus. Okay. So in this case, this is given 106 plus given sulfate 160.0, that is equal to 266 Salmon Cm square mole inverse. So in this way you can determine the molar conductance. If the equivalent conductance is given, then just find out the equivalent conductance of each ion. then just add them. Question is given in molar conductance, so I have written in molar conductance. Next come to question number 2. CH3CO minus 0. Okay, so calculate the degree of dissociation of acidic acid if its molar conductivity is 39.05 Simon same square mole inverse at any concentration, and given lambda X plus and lambda CH3CO minus molar conductivity of H plus ion and acetate ion given at infinite dilution. This much. Then first we have to find out lambda m naught of CH3COH. This is equal to lambda m naught of CH3CO minus plus lambda m naught of H plus. That is equal to 40.9 plus 349.6 in the same 5 okay 750 sorry this is 9 plus 6 5 9 plus 0 that is 9 plus 1 that is equal to 10 0 5 4 4 8 is 9 and 3 390.5. Here you get 390.5. What is the value? 7 cm square mole inverse. This is the molar conductance at infinite dilution, and the another value given 39.05. Then what is the value of alpha? Alpha equal to lambda mc by lambda m naught, that is equal to 39.05 by 390.5. 39.05 by 390.5, that is equal to 0.1. So the degree of dissociation is 0.1. Okay. Next come to question number 1. So this question number 1, this is the combination of so many number of applications of potassium. This is the combination of so many number of applications of potassium. Okay. So given at 291 Kelvin, the molar conductivities of at infinite dilution of ammonium hydroxide, sodium hydroxide, and sodium chloride are this much, and this much. So actually, instead of sodium chloride, this is the NH4. This should be NH4Cl. Okay, this is wrong. Question is somehow wrong. At 291 Kelvin, the molar conductivity infinite dilution of ammonium chloride, sodium hydroxide, and sodium chloride are 129.8, 217.4, and 108.9 Simon same square respectively. If the molar conductivity of a centinormal solution of ammonium hydroxide is much, what is the percentage of dilution? Also calculate the dissociation constant of NH4OH. So this questions carries actually 3 number of questions. So first, lambda m of infinite dilution of NH4OH equal to lambda m of NH4Cl plus lambda m naught of NaOH minus lambda m naught of NaCl. So that Na plus, Na plus, minus Na and plus Na, this 11.4 minus lambda and NaCl 108.9. So if you calculate this, you can find out this value 238.37 cm square. So the value is 238.3 cm square. Okay, next lambda and given at any concentration that centinormal solution lambda m of centinormal solution given 9.33 cm square. Then what is the value of alpha? So here the alpha value is 9.33 divided by 238.3 lambda mc by lambda m naught, that is equal to 9.33 by 238.3. So this value we find out 0.0392, and if you find out in percentage, this is equal to alpha in percentage. So multiply by 100, so that we find 3.92 percentage. Then K equal to C alpha square by 1 minus alpha, and this is given a centinormal solution. In this way, the C value is 1 by 100, or we can get 0.01. That is 0.01, and alpha value given 0.03. We have derived alpha value, and 1 minus 0.0392, and this value we find 1. So the degree of dissociation value we find 1.599 into 10 to the power minus 5. So this is the one question where we can solve three types of problem, three applications of Euler's law. Okay.